Here we are about to continue our proof of Theorem 156, the amazing extension theorem. So far we have proven parts 1 and 3. We proved 3 assuming 2. So now it remains to prove the big part, which I think will take this entire lecture, part 2. So given a countably additive function, countably additive non-negative measure on an algebra of sets, we claim that it can be extended by this outer measure construction. It can be extended to a countably additive function on the collection of mu measurable sets, which, by the way, is a sigma algebra. That's also part of our claim. We already proved uniqueness, so now we're proving that existence and that the outer measure is suitable for this purpose. You might want to pause this screen here and remind yourself about these previous facts that we have available. I sort of reviewed these last time, so I will not review them again. But I'll continue. It's kind of fun to just go here and put a check mark whenever we use something. I think we'll end up using every single one of these at least once. Okay, so let's get started with 2. So let's start by remembering our assumptions. A is an algebra of sets on X, and mu is a countably additive non-negative function on A, also known as a non-negative measure. So you can just say mu is a non-negative measure on an algebra of sets. Then we have 2 goals. Prove A mu is a sigma algebra, and prove that mu star is countably additive on it. So how to prove A mu is a sigma algebra? Well, we already know it's an algebra of, No, we actually do not know that A mu is an algebra of sets even. It could just be some random collection of sets as far as we know right now. I guess all we know about A mu is that it contains A as a subset. That's really all we know. So these are our 2 goals. To prove A mu is a sigma algebra, we really have to do it from scratch. So we have to prove all of the properties in the definition of a sigma algebra. That it's closed under complements, that it's closed under countable unions, and what else? That it contains the empty set and the full set. Well, I guess that part we can get out of the way quickly. Since it contains A, by part 1, we proved it contains A, we know that the empty set and the full set are in there. So it remains to prove it's closed under complements and closed under countable union. But that's not going to be so straightforward. We're not just going to do that in a straight shot. Instead, we're actually going to prove both of our goals by following a kind of complicated plan where we prove little bits of each goal at a time. First, finiteness, the finite versions of the things we need to prove, and then going to the countable versions. Because as we go along, we'll want to use previous steps in this plan. So let me outline the plan here. So here's our plan. It's going to be a 5-step plan. So step 1 is we'll prove A mu is closed under complements. Okay, that's just one of the 2 things we need to prove that A mu is a sigma algebra. Then step 2 will be to show that A mu is closed under finite unions. So eventually we want countable unions because we want to show it's a sigma algebra, but we'll start with just finite unions. And when we do this, once we have steps 1 and 2 done, we will know that A mu is an algebra of sets, at least. Then step 3 will be to actually switch gears and look at our second goal, proving countable additivity. We'll just prove that mu star is additive on A mu. That's actually all we need for countable additivity in this context, because of some of our stuff here. If we can prove that mu star restricted to A mu is additive, then we will know that mu star restricted to A mu satisfies not only the easily satisfied green assumptions here, but it satisfies the white assumptions here. It would be an additive function on an algebra of sets. And so a theorem like this one would apply. Countably additive if and only if countably subadditive. And we actually have countable subadditivity for mu star always. Even in the garbage situation, you always have countable subadditivity. So we would then use the other direction of this theorem to get countable additivity. The other direction, I mean, other than the one we've already used, apparently. So let's go ahead and complete that argument right here inside our plan so that it's clear why we're doing that. So I'll say thus is countably additive. And again, the reason for that is that that puts us into this setting, and then we can use this direction of the if and only if here. And we're also using this, which tells us that we do have countable subadditivity just in general for outer measure, always. So that's how we know that we have countable additivity. Okay, so back here, continuing to describe our plan. Oh, by the way, when we do step 3, that will use step 2. So somehow we'll need a mu's closure under finite unions in step 3. Actually, I take it back. For some reason I thought that was the case, but when I look over my notes just now, maybe not. So maybe the order in which you do these two doesn't matter. But I guess that will be revealed as we get started with it. Okay, so moving on to step 4. Oh, and by the way, once we're done with step 3, we will have mu star on a mu countably additive. So we'll have reached the second goal, right? And then the only remaining thing to prove will be that a mu is a sigma algebra. And the only remaining part of that will be to prove that a mu is closed under countable union. And we even already have finite union. So here we're almost there. So step 4 will be to verify that it's sufficient to prove a mu is closed under countable disjoint unions. So normally you would have to show that a mu is closed under countable unions in general. In step 4, we verify that it's sufficient to only consider unions of pairwise disjoint collections of sets. Or rather, collections of pairwise disjoint sets. So that's not normally something that's going to work. That's going to work here because when we reach step 4, we will already know that a mu is an algebra of sets. So that'll need this sufficiency of considering only disjoint unions here requires already knowing that we have a closure under finite unions. And then finally, step 5, a mu is closed under countable disjoint unions, which in step 4 we argued was sufficient. Therefore, a mu is closed under countable unions, and therefore it's a sigma algebra. And that was our other goal that we needed. So there's our 5-step plan. We'll carry these out, and if we succeed in all of these, then we will have proven the amazing extension theorem. So let me separate these out into separate videos, maybe some of them, maybe merging some of them, and let's get started.